In this Lemma 4.5, we said that if there exists a class KL function, right? KL function beta, and beta is a function of x and t, two elements, right? And for a class KL function, it increases the first element and decreases with the second element, right? So if you imagine that beta is on this z-axis, right, and the first argument is in the x-axis, and t is on this axis, and you can see that beta function will increase with x, right? So it increases with x, but decrease with t, right? So the configuration is like this, right? Increase if you start from here over here. If you fix x, right? You fix x, and you increase t, then its beta value will decrease, right? And if you start from here, again, for a larger x, or you can imagine that for in this case, for a larger initial condition x0, right? You can start from a higher value of beta, and it decreases along with time. So now, in here, okay, in this condition, because xt0 is a initial condition, right? So it's a fixed value, right? It's a fixed value. So that means you can pick up any, if you start from here, x t0. Okay, this value is in the initial condition here, which is a constant, which implies you already pick up some beta function with this value, right? Now, what is time variant is this t, right? You increase t, and you can obtain a beta value that decreases with time, right? And this plot, this contour is this contour because this is the slice of this configuration, right? Can you imagine here, right? You fix x, increase with time, so it increases with time given some initial conditions. Okay. So this is beta function, and the xt, which is a function of time, is bounded by this beta function, which means the xt is somewhere under this red line. Now we're trying to explain what is KL function and what does this mean. So what is KL function? KL function, according from previous lecture, is the definition is it had two elements here. Okay, beta function. You have two elements. The first element increase, the beta function will increase along with the first element, but decrease if you fix first and increase the second one. Right? That's KL function, beta. Okay. So class KL, the definition for class KL function is a continuous function beta. Okay, it maps from two domains into a scalar domain. Okay, so you have two arguments, r and s, and it has two properties. If you fix s, if you fix the second element and increase the first element, then beta increase with r. Okay, and again, if you fix r and increase s, the beta value will decrease to 0 as s increase. If you say, given the beta function, if you fix t, this function will increase with x, right? This plane, this is in this plane, x beta plane, okay? So increase with x, okay? And in this case, x is the r on the slide, right? Now, if you fix the first element x, okay, increase with time, it will decrease. 这样没问题。不同 if you start from different x. So this intersection is generated by fixed x. X is fixed on this plane, right? It's an intersection on the beta t plane. It's on this plane. Okay, it's projection on this plane. 听懂吗? This is on a 2D plane. Okay, formed by this axis and this axis. This is on another 2D plane, which is on this t beta plane. Okay, 懂吗？听懂吗? So according to this definition, right, beta increase with r. So, or you can say it's r. So beta will increase with r, right? Right. Decrease with t, right? So if you start from here, you have decrease. This is a beta function, right? And now we substitute, given some initial condition x t0, it's a constant, right? Means you can pick up any x t0, say here, right? Now the next step is we increase t, okay? We increase t. Then we know that if you start from here and increase t along this direction, right? Beta value will decrease, right? Okay, and if xt, if you find some solution xt, that this always the lower upper bounded by this beta, which means the xt is somewhere under this red line, right? Because it's upper bounded by this beta, right? So if this solution is upper bounded by this red line, it guarantees, then it says that this solution, okay, the solution along this dynamics is uniformly asymptotically stable because it will converge to 0, right? Uniformly. It doesn't depend on time. So the reason that beta increases with xt is if you pick up a larger initial condition, right, the beta value will be higher. Okay. So the higher the value of this, so such that you can upper bound a higher initial condition of x. That's the reason why we define KL function. Because this is the so you pick up initial condition constant, right, and increase with time. So this plot is actually this configuration, right, along this 2D plane. Okay, that configuration is this configuration x. Okay, so what this lemma says is, given some initial condition, okay, it always decreases with time, and eventually it will go to 0. X t norm will go to 0, and this initial condition is x t 0 norm. Oh, okay. So maybe it's hard to understand from here, but you can imagine, it's easier to imagine from these plots, right? Okay. So now, so theory 4.8 is from Clear's book. Okay, so given some x0 to be an equilibrium point for some nonlinear dynamics, okay, D is the domain for the first argument x containing the origin. Then we choose the v function that maps from this domain to another and this domain to the other domain because it's a scalar function. And v had to be continually differentiable, otherwise v won't have a solution, or the solution might not exist, okay, or might not be unique. So if v satisfies this condition is lower and upper bounded by some autonomous PD functions, W1 and W2, okay, and its time derivative is an SD, less or equal to 0, you can say that the solution of this system will be uniformly stable. Okay, so this condition is kind of like V is PD compared to the autonomous case, right? V is PD and V dot is an SD. then you can obtain that system is stable. But because we have uniformly here, because we are now discussing the non-autonomous case, which is a function of time, right? If the convergence doesn't depend on time, then it's uniform. Okay? 能懂吗? Any questions? So it's uniform. Basically, it's from here. W1 and W2 doesn't depend on that did not depend on time. Okay. It's hard to see from here, but I will give you an example, and it's easier to understand. Okay, in a few seconds. And this theory 4.9 is more. The conclusion is that the system trajectory x of this nonlinear dynamics with equilibrium point x equal to 0 is uniformly asymptotically stable if you replace the previous condition, previous lemma, by this minus W3. Okay, so W3 is a PD function. With the minus is a negative definite function, and it's non-autonomous because it doesn't depend on time. Could you give me an example? Could you give me an example of this V? And the lower and upper bound is x1 squared, y1 squared. This is true, right? This V function can be lower bounded by this, upper bounded by this, for sure, right? But what's missing? Because V is a function of time. Here, nothing is a function of time. There's no time element, right? So let me add some stuff. So now it's a function of time, right? And can you find some PD function that upper bound this? Can you? 可以吗? So what is the upper bound of this function? 1, right? 1, right? And lower bound is what? 1 over 2, right? Right. 对吧? So this is same as this, okay? 能懂吗? So if you plot this out, sorry, let me reduce to just x. Otherwise, it's hard to draw a 4D plot in here, right? Okay, just x, 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 and this is t. Okay. So what is W1? W1 will be maybe this. Okay. It's the lower bound of W. It's the lower bound of V. So V, let's say V is here. And W2 is the upper bound. So it will be on top. So this is V, this is W1, W2, okay? At t equal to 0, right? Okay. So we know that W1 doesn't depend on time, right? W2 also doesn't depend on time. Okay, so you can find that it will be constant. So imagine that no matter what time, what t is, okay, v is a time varying function. It might be somewhere in between, but it's always upper and lower bounded by W1 and W2, right? And what's the second condition? The second condition is V dot, which equal to that. Okay, so it means this V, if you start from maybe your initial condition is here, x0, okay, then V dot is negative, definitely, right? So V will decrease, and the decrease rate it doesn't depend on time, right? Right. So this value is V at when V equal to T0, the initial condition, and when T is 0, right? The value is his. And this value will decrease with time because of the condition, right? 对吧? So eventually, so when will this V stop decreasing according to the condition? When will it become 0? When? 什么时候它会变成0? Only when x is 0, right? Because it's PD function. The only condition for this to be 0 is what? X equal to 0, right? For PD function, right? PD function can only be 0 at 0, 对不对？对吧？你现在把以前用的东西再连贯起来 right? PD function defined as is 0 at 0. So this function is only 0 when x is equal to 0, right? Right. Okay. 好吗? So when will it start decreasing? Only when x equal to 0, right? So when it's equal to 0, when x equal to 0, what is this? 0. And its upper bound is 0. So V must be 0. Then you know x must be at 0, right? That's why it's asymptotically stable uniformly, because the decrease rate doesn't depend on time. Okay? PD 记得吧 0 at 0. Zero at 0. Okay. So V dot is upper bounded by a negative PD function. So when it start decreasing means V dot is 0. So for this to be 0, x will be 0 because it's PD function. Yeah, 懂吗? Again, we don't know the solution of x. So we discuss the V functions. Right? We find it had been lower and upper bounded by W, right? By W1 and W2. And V will decrease, which implies somehow x will decrease. This says V dot is negative definite, right? So it means V have to decrease. But it's lower bounded by some PD function, so it cannot be negative. The minimum value of this will be 0, right? and this eventually this is also 0. So v had to be 0. And the only chance for this function to be 0 is x to be 0, right? Not this, because it's lower bounded by some PD function, which doesn't depend on time. Okay, the minimum value of this function is 0 because it's PD function. 不是有写过作业吗？它最小值是多少？0嘛。0的时候它在哪里？原点吗？对。And the proof for theory 4.9, here is a more systematic procedure, right? But here is just my explanation. So the standard way to prove this is, okay, this is the condition. 1 and 2 are the conditions, right? For theory 4.5, 4.9, right? But the proof procedure will be this. V is upper bounded by alpha 2, right? Which is a class K function, okay? And using these two conditions, you can solve for V, right? For example, if you find some nearby function defined as this, and after you substitute the dynamics, after you substitute the dynamics to find V dot, and you show that V dot is negative, okay, if you find this, can you solve for V? Yes, you can, right? You can substitute this back to here, which means V dot will be, so you know this is V, right? So V dot will be minus V, right? So it's a linear ODE for V, not for X, right? For V. So it can find eventually V, which is a function of, it's just a linear ODE, so you solve, the solution is this, okay? The solution for VT is this, based on this ODE, okay? Right? But it's V, not for X, okay? The relation between V and X is this, okay? 懂吗? It's upper bound, not equal, okay? So what does this mean? So if so given the dynamics, and I know the initial conditions, it's no way to find out what's the solution of X, right? Okay, give you some nonlinear ODE, given the initial condition, can you find the solution? No, right? If it's a linear ODE, that's fine, 对不对？就像这个是 linear ODE 嘛。So for linear ODE, for example, 你发现你好像没办法从数学跟那个数字连贯，对不对？你们是有这方面比较还在不习惯，是不是？是吗 ？For linear case, nonlinear case, ODE， 例如这样，这你会解吧？对不对 ？This is linear ODE. Everyone know what's the answer of X. If I give you a nonlinear ODE, can you solve the solution for X? Can you solve for this? Yes, right? Can you solve for this? By hand, not by the computer. Usually not. This is just one of the nonlinear example, right? Okay. So you don't know the trajectories, right? 对不对？对吧？对吧？ Okay. But we don't know what is the trajectory for x1, x2, but we know the trajectory for v. And the relation, and v is upper bounded by some function of time with initial condition v0, right? So that means based on this, okay, given v0 initial condition at t equal to 0, this is 1. Okay, so it decreases from here to 0 exponentially fast, right? So this is vt, this is vt, okay? And given vt, you can find x, right? Given vt, you can find x, right? But this is the upper bound of v. This is the upper bound of vt, right? Upper bound not equal. 所以你的 x could be somewhere in here, x norm. 因为这是 norm 嘛 v equal to x norm square. Okay. 听懂吗？听懂不懂？ So you actually, even if you use the above function approach, you don't know the solution of x. But I know the norm will be upper bounded by these trajectories. Okay. And remember so the next step is, so this is one of the disadvantages of using the above function approach. Okay. If you consider it's a disadvantage. But the advantage is you can prove stability, right? Eventually it will go to 0 because it's under this contour, right? X norm under this contour, and this contour will goes to 0 as t equal to infinity. Okay. 这样没问题。So next topic is you will be uniformly or ultimately bounded. So given some differential equation, okay, a linear differential equation, you can solve for the solution. Okay, in this case, you can solve for the solution. And the upper bound of this solution is a exponential minus t0 plus okay. So again, it's this absolute value of x is upper bounded by some trajectories. So these trajectories, so this part will decay to 0 as t go to infinity, right? So the first power decay, it goes from A, it starts with A, okay, because when t initial condition, this is 1, so it decay from A to 0 as t go to infinity. And this, what's this? Initially it was 0, right? But eventually it goes to sigma. Okay. So when you sum up these two, you will get the upper bound of xt. Which is what? Which is here. Something like this. Delta, okay, delta. Delta. Okay. So it doesn't converge. So xt doesn't converge to 0, but it also doesn't go anywhere. It doesn't go to infinity, right? It's approaching this delta value. Okay. So we say it's uniformly because the decay rate is exponentially fast. So we say it's uniformly. Okay. Uniformly, ultimately bounded, because eventually it's converged to this. So you can say it's bounded by some constant. Okay. So what if a dynamics is highly nonlinear? Highly nonlinear compared to this one. Okay. This one is easier, right? It's kind of here is linear, right, and some time element. But what is given a dynamics that's highly nonlinear? And solving this, for example, like this, delta times sine t and cosine t, then it's hard to obtain the analytical solutions, right? So, then this way, solving this differential equation is quite impossible. So another way is we want to look at the v. Okay, we discuss the dynamics of v of a variable function. Okay. So if you find some v, okay, and take a time derivative on v by substituting these dynamics, okay, eventually you got this form, which is similar to this, kind of like this. So there will be three cases. There will be three cases. If your initial condition, so look at here. If your initial condition x, so beta, this delta is a constant. Okay. If your initial condition x is greater than delta, okay. If this x is greater than delta, so this equal to this, right? They are the same, right? This equal to this. So if you're, in the first case, if your delta is greater, if your xt0 is greater than the delta, okay, then this is positive. So say it's delta here. If you start from the initial condition that is greater than delta, okay, then guess what? Will it go up or go down? Decrease or increase? For v x norm. This is x norm. Yeah. So will it go down or decrease or increase? So if this is greater than this, v down will be negative, right? So the xt norm will decrease. And when will it stop decrease? Only when this equal to delta, right? So it will decrease, stop or remain a constant only it reaches, this x reaches this delta, right? So this covers the first and second case. Now go to the third case. If you start, initial condition is under this delta, okay, it will increase, right? Because this is negative and negative, so it's positive. V will increase. V increase means the x norm increase. So it will increase until when? Until the second condition, right? Until the second condition. Okay. So no matter if you find that V is like this form, okay, no matter what your initial condition is, x norm will eventually converge to a constant, and that's the UUB. That's the UUB case. So this form, okay, remember this form. If you have this, that's great, that's negative definite, right? But if you have another term, that usually caused by disturbance or some unknown unmodeled dynamics, right? Then you will have this term that result in the system trajectory to be UUB, okay? So in other words, it prevents the system converge asymptotically, okay, because of disturbance, unmodeled dynamics. So here I miss the t, this axis is the t-axis, time. Let's discuss the homework problems. Homework solutions. The first question, or as the question is, what is equilibrium point, right, given some dynamics? Well, some people, some students said equilibrium point is the point that if you start from degree, but it's not the definition for equilibrium point, right? If I ask, what if I am not starting equilibrium point, then what's the equilibrium point, right? 懂我意思吗？这边是说，如果你从 equilibrium point 开始，它会一直在 equilibrium point， 那我还是不懂什么是 equilibrium point。如果我不从 equilibrium point 开始，那我会收敛到哪里？我会收敛到那个是 equilibrium point 吗？对 ，so 有一些人会有这个问题，那我就给他错，因为 equilibrium point 应该是说，不管你从哪里开始，它最后会收敛到 equilibrium point。那它的 the definition, the formal definition should satisfy this. If you say this, then you are done, okay? X is the equilibrium point. This is a very simple, compact, powerful expression, right? It tells more than 1,000 words, right? 你看你写这么长还不一定得分，对不对？你就写这样就好了，对吧？或是 someone says, equilibrium point is, then 这个是 equilibrium point， 这样也不算对。为什么？这个跟这个 x1， 这个 x 跟 x1 是一样的吗？ Are they the same? Not really, right? If you say x1, oh, then I understand it's x1 satisfies this condition, right? So if you say x and say x1 is the equilibrium point, there's no relation between the two, right? 懂吗？ Okay. So this one should be simple. And another question is, if a system is convergent, does that imply stability? Stable? Well, it's not necessary, because what is the definition for stable? Stable means if you start from x0, you start from here, right? Eventually, that no matter where you go along with time, you remain bounded in this radius. Okay. Epsilon. And the radius disk, the region of radius that the initial condition is started from is the radius of delta epsilon. Okay. Then you can say it's bounded. So you start from somewhere, and the trajectory will remain bounded by some finite radius that it says bounded, okay, for all time, okay. But convergent means you can go from here but go to somewhere greater than the radius, greater than this larger radius, and go back to 0, right? It only care about this, if convergent only care about if it goes to 0. It doesn't care about where it goes during the period, okay? 这样懂吗? So this is usually convergent also sometimes also implies asymptotic, right? Okay, and this is stable. So AS asymptotically stable means it had to be stable and convergent, right? So for AS, you have to satisfy this. Okay? It cannot go outside. You have to remain bounded for all time and converge to 0. 这样懂吗? 好. So in this slides, we discuss the behavior of the solution X, right? Based on the dynamics of V, okay? So from V, we can use it to infer what a potential trajectory of X, okay? So given some trajectory of V, okay, you can use to tell what the potential location or trajectory of X norm. Okay, if this is a V, and there's some relation between this X norm with V. So if Vx is x1 squared plus x2 squared, as we mentioned before, this is the X norm, right? So if the Vt decrease along with time, okay, we can infer this to this X norm. Okay, because it's equal sign, right? And if you find the trajectory of Vt by solving V and V dot, right? So by solving the ODE, you can find the trajectory of this V. And because it's equal sign, this represents the norm of X, right? Okay. But what if, now if I change this to 2, okay, if I change to 2, then this no longer holds, right? 对不对？就变成是它的 level set 变成是椭圆的，对不对？就是from homework 1, the level set will be an ellipse, right? So if you given this V trajectory, can you say that the X norm is same as V? No, right? 对不对？就不是了，能懂吗？ Remember the question I asked you in the homework. So and I said a few weeks ago that some people say like find this, and I can say, oh, X is bounded by the similar trajectory. That's not correct, okay, because of these coefficients. 能懂吗? And because it's norm, so if that's fine, then again, it's norm, right? Norm is defined as x1 squared plus x2 squared, okay? So where's x1? x1 could be anywhere from here. x2 could be some value from here, okay? We don't know the trajectory. We only know the upper bound, okay? This is the second misconception. The usually people were confused with this, okay? 能懂吗? Okay. So usually what will you do with this? If you given this 1x1 squared plus 2x2 squared, if you want to know this, what will you do? I would say what you can do is, okay, you keep norm here and put another coefficient 2 here. Okay, 懂吗? So you put 2 here, then you divide the v by 2. Okay, you move 2 to here. Move, so this the half the value of v, which is around here, will be the upper bound of x norm. Okay, so the difference so here are two definitions. One is uniformly bounded. One is uniformly ultimately bounded. What's the difference? The difference is here. Is in here. Okay. Uniformly bounded means if you start from a radius smaller than a, then the trajectory, the normal trajectory is always bounded by beta. Okay. The second, the UUB is you start from the same radius within the same area of the same radius, and it will converge. The trajectory will converge to a value b over, we used delta before, okay, within some final time. This is UUB, right? Eventually it will converge to some value delta. Okay, and b can upper bound the delta, okay, in some final time. Capital T is some final constant. Okay, so it's T plus capital T. 这样. For uniformly bounded, you can go here and oscillate or go up again. Can go up again, but it still remain bounded by some constant, by some larger radius. 能懂吗？有点复杂，对不对？但是它最终就是 bounded， 不会再超过这个 bound， 这样。Okay, eventually you would be under this upper bound. Okay, but for uniformly bounded, it can go up to some predefined bound, but remain bounded by some larger bound. This UUB bound usually is caused by some disturbance or unmodeled dynamics. Okay, so if you increase the control gain, you select a larger control gain, you can reduce this UUB bound. Okay. Any question? So the next time when you see UUB might be when you read in the papers. Okay, at the time you will understand what is the UUB, because that's very obvious. Okay, so keep this definition in mind, in your mind. Okay, and it's just definition for you. Okay, it's not a tool; it's a definition. You don't use this to design a controller. You will never do this. Okay. But you can see this on the paper because of the definition, but it's not a tool. Okay? 这样 OK 吗？好。So next will be the last topic before we go into the controller design. Okay, this will be the last topic. So it's called Barbalat's lemma. And before we talk about Barbalat's lemma, there are some usually there are some common misconceptions, which means that usually you think it's true, but it's not. Okay. So the question is, if I say that f is a continuous function. If its time derivative approaching 0, do you think f is at that time? Do you think f will converge to or have a limit? Will it converge to a constant or have a limit? Yes or no? If f dot is approaching 0, did you think f will converge to a constant or have a limit? 你觉得呢？ Yes or no? Five years ago, I don't know. Okay, now I know. So the answer is no. 5 years ago, when I was a graduate student, I don't know. Okay, because it's not the area of mechanical engineering, right? No one asked you this kind of question before because usually it's from the math department, right? They discuss about this fact, but it's not for College of Engineering students. So it's not. Why? The counter example will be this. If x dot equal to this, and the solution ft will be sine some log t. So as t goes to infinity, okay, this argument in sine function will never reach to some constant, right? Because it's a sine function. As this log t increase, sine never reach to a constant, right? It always oscillate, right? But this f dot is approaching to 0 because t goes to infinity. 能懂吗? So second example is this. Again, as t goes to infinity, f dot is approaching 0, but ft never have a limit because of the sine function here. Okay? So this is the misconception, and that will be used to prove Barbalat's lemma. Okay? So the first example, the ft were looking like this. Ft, okay. So initially the frequency of oscillation is higher, but eventually it's slowed down. And it looks like approaching to some limit, but it's not. Okay. You just reduce the frequency. Okay. Second one is similar. Okay. Because log t is in the sine function. And the second misconception is the reverse. Okay, the previous one is f dot approaching to some 0. Now, for f approaching to 0, it doesn't imply f dot will approach 0. Okay, 能懂吗？当你 f 趋近一点的时候 ，f dot 不一定，它的微分不一定是0。Okay, again, sine function or cosine function. So if ft is this exponential minus t, exponential power to the minus t, and sine exponential power to the 2t, this will approaching 0 because of the first term exponential power to the minus t. Okay, but the time derivative never reach to a constant, never reach to 0. Okay. 这样没有问题，很无聊，对不对？好，再来 Barbalat's lemma, the last lemma before we head into the controller design section. So what is Barbalat's lemma? So we have introduced the Lasser's theory, but that's only for autonomous systems. A systems that don't explicitly depend on time. But for how about if I give you a non-autonomous systems, can you use and you have the similar conditions. V is PD, but VDA is NSD. What theory can you use? Because Lazarus theory is only for autonomous systems. Now you have a similar situation, but for non-autonomous systems. Then the theory to apply is Barbalat's lemma. Okay, so that's why we discuss the time derivative here, because non-autonomous system usually consists with arguments of time, right? 通常它的 dynamics 是 explicitly depend on time. Okay. So Barbalat's lemma says here are the two forms. Basically, you can use one of the two. Okay, both are true. If ft is uniformly continuous and limit when t goes to infinity, the integration exists. The integral of ft exists and it's finite. Then you can say ft this will converge to 0 as t goes to infinity. Okay. So now look at this. So the second version is the non-integral form. Okay, there is no integral. In other words, you take the time derivative on f, which is f dot. Okay, take the time derivative on this integral, you got f here. 懂吗？就是这个是它的，这个第二个是它的微，把第一个微分就对了。And the second one is similar to you take a time derivative on this part, then you got this part. Okay. So it's called non-integral form. So it says if f dot is uniformly continuous and the limit of f exists at t go to infinity, then the f dot will goes to 0 as t go to infinity. 能懂吗? Then this says, so this clear out the condition for these misconceptions. 能懂吗? In other words, 也就是说，如果你要让这些 misconception to be true, okay, for this misconception to be true, you need other conditions. That is, f dot had to be uniformly continuous, and f is bounded. 懂吗? That's Barbalat's lemma. F dot had to be uniformly continuous, and f, the limit of f exists and finite. 能懂吗? So the misconception, the previous misconception don't have these conditions. Okay. 为什么不是 uniform continuous? Okay. F dot 这个 uniformly continuous 我想一下 uniformly continuous uniformly continuous 是说它的微分是存在的，你把这个东西取微分，它有可能不存在。The time, so uniformly continuous means the function, the time derivative of this function exists. So when you take the time derivative of this, it might not exist. Okay, you can try. Okay, 你回去可以 try 一下。Okay. Okay. So this is Barbalat's lemma. Okay. And this lemma has been used to prove the stability of non-autonomous systems. Can you imagine? 有办法想象吗？这怎么用？ Can you imagine how will you apply this? Imagine maybe 50 years ago, you know this theory. You are Barbalat, and you invent these two theories. How will you apply? You are not a control engineer or a researcher from the College of Engineering. 你不是工学院的 okay? You are from mathematical background and you invent the theory. How will you apply it to the real engineering problems? 50年前，几十年前我忘了 maybe 50 years ago, long time ago, okay? When you are still not in this world, maybe, okay? How? Imagine. 讲一下这个怎么用在控制上面，证明稳定性。How will you use this to prove the stability? So now is the chance to be Barbalat in 10 minutes, okay? 你觉得呢？ So obviously we want 0, right? 0 here is 0 here. Because convergence, right? –顺便可以休息一下，怎么？ So uniformly bounded means, okay, you take this one, f is uniformly bounded if and only if the time derivative is bounded. Belong to L infinity means it's bounded. The largest value is bounded. Okay. So, so the L2 here, the L infinity, the definition for L norms is, for example, for L2, okay, for L2, we say a function is L2. We say a function is L2 if the second norm is bounded. Okay. Well, if we say a function is LP, it means that the P here, you say P could be 1, 2, 3, 4, 5 to till to infinity. So we say if the F is L2 means you put P by 2, okay, and this value exists, then we say it's L2. Okay. In other words, for L2 function, the square of this F function have to be bounded. The integral of this F square function have to be bounded. Okay. If F is this function, okay, what is this for P to be 2? What do you think? The integral from 0 to t of F square, right? F square, 对不对？懂吗？ So if this is F, what is F square? F square, okay, square. Square. You move this to be negative will become positive, and square the no. F square means some function here. Square, square. So, right? 对不对? Okay, and you take the integral of this with respect to time. Square, well, it doesn't matter whether you put the absolute value here because it's square. So from 0 to t, you put f squared. Basically is the area of all these pieces, right? If the summation of all these areas are finite or exist, then it's L2 function. And here is some properties. F1 norm is upper bounded by F2 norms and until F infinity norms. Okay. So, for example, here is the case that we apply Barbalat's lemma. Okay. So, given nonlinear dynamics here, nonlinear non-autonomous dynamics, because here you see the t components, right? And theta is the estimate error of theta tilde is the estimate error of theta, and theta hat is the estimate value of theta. Okay, so this is the estimate error. So given these dynamics, we choose a default function to prove stability. Okay, so we choose this default function. And after you substitute this to this time derivative, the v dot, okay, you substitute this to v dot, you got v dot equal to minus kx squared. Okay, so it's ND or NSD? It's NSD, right? Because in your v, you have x squared and v tilde, theta tilde squared. But here, apparently, theta tilde squared disappears, right? So it's NSD. So this is the similar situation when you see the case that we apply Lassalle's theory, right? The time that we discuss invariant set, right? But the only difference is here we have time elements t, okay? Because this is non-autonomous case. So we have to use Barbalat's lemma. Okay, V is PD, V dot is NSD. So what for this condition, for this V to be PD and V dot is NSD, what's the message that you got? That is V is bounded, right? 对吧？记得吗？ Why V is bounded? Given this and this, why V is bounded? Can V increase? 可以吗？ V 可以 increase 吗？ No, because the largest value of minus k squared is 0. 0 means V dot is 0, which means V, the worst case is V is constant, right? Either V decrease or V holds a constant, right? It cannot increase. So V is bounded. So if V is bounded, X will be bounded, theta tilde will be bounded because it's PD function, which means you have square here, right? 对吧? So if this is bounded, all the arguments have to be bounded, right? So these two are bounded. Okay. So the second thing is according to dynamics and 1, okay, 1 and this dynamics. You can say X dot is bounded, which means X is uniformly continuous. 对不对? So because X is bounded, X dot is also bounded, so it's uniformly continuous. X is uniformly continuous. 懂吗? 刚不是讲过了 uniformly continuous 就代表它的微分是 bounded 的嘛？对啊 So this 1 and 2 condition means X is uniformly bounded. So I know X is uniformly bounded. Can I show X converge to 0? This is the key question, right? So next, according to this, okay, we can show X goes to 0. According to this, we know that X is L2. What is L2? This. The square, the integral of this is bounded. Right? Why? What's the integral of this? Or let me say, what's the integral of this? V. The difference of V is the integral of V dot. Right? 懂吗？ So 50 years ago, that's is this three, this is the application, and his theory can be applied on this kind of problems. And how you convince people is you propose these three conditions, the three facts associated with the Barbalat lemma. Then it become history. Okay. Why this implies X is belong to L2 function. Okay. See, L2 means the integral of the square of the function is bounded, right? So to prove X is L2, you need to integral L2 with respect to time. If it's bounded, means X is L2, right? Right? Okay. How did you show this? Use this condition. V T X equal to minus kx squared. You take the integral. Is this one bounded? If it's bounded, it's L2. So it's hard to see from here, but let's look at the left-hand side of the equation. It's easier to tell whether it's bounded or not, right? Because what does this say? This equal to what? V T minus V0, right? 对不对？是吧？这是积分嘛？积分以后你就把 dot 拿掉了，代入上下限。对 ，v 大的积分是什么？不是 v 吗？代入上下限不就是 difference 吗 ？So is this bounded？ 是吗？它是 bounded 的吗？这是什么？这两个东西相减吗 ？What's this? So we know that so given some x0, if you start from some initial condition, right, which implies your v start from some value constant, right? Constant value, right? And v will decrease, right? According to this, v had to decrease or remain constant, right? The worst case it remain constant. So it cannot go upwards. It had to decrease, and maybe at somewhere when x equal to 0, it holds a constant, right? So this is Vt. So the largest difference from the initial condition to here, so you can say Vt can be anywhere in here. So the difference between initial condition of V and Vt will be bounded, right? So this is bounded, 对不对？这是 bounded. So if this is bounded, this is bounded, then L is L2 function. Okay. Now you can use Barbalat's lemma. X is uniformly continuous, and X is L2. So X have to go to 0. 能懂吗？ 懂吗？也就是说 ，if this is xt, you start from xt0, okay? We know that x dots. We know x is bounded. Okay, it's bounded. It's bounded between maybe some value here. Okay, it's bounded, and x dot is bounded. So the slope of this configuration cannot be infinity, right? And what? This condition says what? The area, the square of this function had to be bounded, which is similar to this area had to be bounded, right? So for this area to be bounded means this value cannot go anywhere other than 0 eventually, right? 对吧？如果这个 area 不是有限的，它这个东西一定会，如果这个东西到0的话，应该说，如果这个 area 是有限的话，它一定没办法走到无穷远嘛。对，它如果走到无穷远，它 area 可能就是无穷大了嘛。是吧 ？If a function goes to, if this function x doesn't go to 0 as t go to infinity, then the area will not be finite, right? Right. If x, let me say again, if x doesn't converge to 0, means you always have a gap, right? If you always have a gap, this area can go to infinity. Right, which break this condition, right? In other words, you cannot have a gap as t go to infinity, means x go to 0. Okay? 所以 Barbalat lemma 就是这样用，就是用在 x， 就刚讲，只是说你怎么把它 connect 起来，就是不是10分钟就可以搞定的这样。Okay? So this is for non-autonomous case.